Hey, let's take just a minute to consider resonance structures. We're going to look at two examples. This is the nitrate ion, NO3 minus. This is the phosphate ion, PO4 3 minus. Now, in both cases, if you try to draw them using the normal rules, in other words, nitrogen tends to form 3 bonds and have 1 lone pair, whereas oxygen tends to form 2 bonds and have 2 lone pairs, well, it just doesn't work. When they actually analyze the structure of the nitrate ion, they find that all the bond lengths are equal. This is the best you can probably do to show what the structure looks like, but it fails in many respects. The bond lengths are equal for each nitrogen to oxygen bond, but this one would predict that the double bond would be shorter than the other two. This is where we invoke something known as resonance. These are the double-headed arrows here, and what we say is this is an average of these three structures. Nothing is happening when we go from here to here to here. We're just doing a little experiment in our mind, if you will, where we're saying it's the average of these three. Some people think you'd be better off drawing dotted lines, saying that the bond order is, I think, perhaps 1 1/3 for each one, where that double bond is spread out between the three bonds here. However, this works reasonably well, and it helps organic chemists understand things. I'm going to draw how one might show the electron flow for each of these, not really by drawing it, but by just moving this arrow here, and hopefully this can give you some idea of what's going on. I'll do the same thing for phosphate, and will be the total treatment of resonance for this course, which is pretty brief, but let's have a look. I did choose these two selectively because you may see them at another time. Okay, so here's the nitrate anion here. The minus charge is distributed. Now when we go from here to here, can you see how this single bond becomes double and that double bond becomes single? Don't forget that a line represents a bond, which represents 2 electrons. So let's take these 2 electrons, throw them in to form that new bond. So we're going to go like that. Boom. Now, if we did that alone, we'd be taking electrons away from this oxygen, giving it a positive charge, and throwing them onto that nitrogen, adding, in effect, 1 electron to that nitrogen, giving it a negative charge. However, simultaneously, we're going to take 2 of these electrons and throw them up there. Therefore, the amount of electron density around nitrogen does not change. Some is added, some is removed. However, it does change here and here. So think about that. There we are forming the double bond. Here we are forming the electron pair. So we'd have a negative charge here and no charge there, hence -1. Think about how you'd go from here to here. Just look at what's double and what's single. Well, we are making this bond single and we're making this bond double. So I hope you could see that if you drew an arrow from here on to there, we are making a double bond, and if we take that bond or perhaps this one, and throw it on to there, we're making that single. These are the resonance structures of the nitrate anion. Here's the phosphate anion. Now, each one of these actually has a 3 minus charge. It's pretty easy to see where they are when you understand that here is when oxygen has 1 electron too many. It has 6 valence electrons, but if you count it like this, 2, 4, 6, and the one that is shared, that makes 7, hence a negative charge. Convince yourself that these oxygens, double bond and 2 lone pairs, don't have a charge. Oxygen has 6 valence electrons, and we have 1, 2, 3, 4, and the shared ones, 5, 6, we're good. Okay, so -1, -1, -1, that's where the -3 comes from, the phosphate. Now just try to imagine how we'd go from here to here. I'll do it for each case and then we'll be done. I need to make this bond double and that one single. So I'm going to go whoosh, whoosh. To go from here to here, I will go, let's see, I need to make this one double and that one single. So I'll go whoom down to there and whoom up to there. For this one to this one, can you see what the mechanistic arrows would be? Looks to me like we want to make this single and that one double. So we're going to go from here whoosh, down to the bond, and from the bond onto the oxygen atom. And those are 1, 2, 3, 4 resonance structures for the phosphate trianion, indicating that each phosphorus to oxygen connection really is about 1.25, 1.25 bonds rather than single or double. The double bond is distributed evenly between those 4 atoms. That's a very brief introduction to resonance.